Imagine standing on a planet so new it has not quite figured out how to be a planet yet. Earth, in its earliest moment, is less a world and more a cosmic construction project with absolutely no safety regulations. If you were somehow dropped into this scene, preferably in a fireproof spacesuit with a very generous insurance policy, you would witness a globe that looks like it rolled straight out of a star's workshop, still glowing from the heat of its own creation. Lava surges like ocean waves, continents do not exist yet, and the sky is a swirling haze of gases trying to decide whether they want to be helpful atmosphere or dramatic special effects. In other words, Earth is basically a baby dragon pretending it is already full-sized. This chaotic era, known as the Hadean, spans the first 600 million years of Earth's existence. And the real trick? We can hardly prove anything about it. Most of the rocks from this time have either melted, vaporized, or been crushed beyond recognition. Earth is that friend who deletes their search history so thoroughly that even the device starts questioning whether it ever existed. Scientists have spent decades trying to piece together what the planet was doing back then, but the Hadean left behind so little evidence that studying it feels like trying to reconstruct an entire movie based on 3 surviving popcorn kernels. You know something happened, but good luck figuring out the plot. Still, even in all this uncertainty, the Hadean era sings with possibility. This was the messy, explosive phase that shaped the world we now walk on. Before oceans shimmered, before continents drifted, before life fluttered its first experimental molecules, there was only heat, chaos, and an atmosphere that probably smelled like the universe's worst soup. But it is here, in these first violent chapters, that the seeds of everything familiar were planted. Earth had to be scorched, smashed, and reshaped countless times to become the calm, blue marble we now politely call home. It is weird to think about, but our planet's earliest chapter reads less like a serene nature documentary and more like an action movie where the explosions never stop and the main character keeps dramatically reinventing itself. One reason the Hadean era remains so elusive is because Earth was constantly wiping its own memory. That molten surface was a geological etch, a sketch that kept getting shaken, making every clue vanish just as quickly as it formed. If the planet had a diary from this time, it would be one long scribble with occasional scorch marks. The oldest solid materials we can find today are tiny minerals that survived purely by stubbornness, the geological equivalent of someone clinging to a doorframe during a hurricane. Everything else? Gone, melted, recycled, or flung into space by impacts that would make even asteroids think twice before showing up uninvited. And yet, even with these gaps, the Hadean has a strange magnetism. There is something beautifully human about wanting to understand a time that actively refuses to be understood. Scientists chase it the way detectives chase cold cases, looking at fragments, chemistry, simulations, and the occasional mineral that seems to whisper, "Well, I remember something." Part of the joy is that every small clue feels like a victory. The Hadean may not want to be remembered, but we are determined to remember it anyway. This era also forces us to rethink what a planet's beginning should look like. Popular imagination often paints young worlds as gentle, peaceful orbs slowly cooling while the cosmos hums softly in the background. The truth is closer to a rock thrown into a cosmic blender and set to maximum speed. Yet somehow, out of this inferno, stability eventually emerged. Earth stepped out of the furnace with the raw ingredients it needed to become a habitable world. It is almost poetic that our quiet blue planet began as a lava-spitting chaos gremlin. So as we begin this story of the Hadean era, think of it as the most dramatic prequel ever made, one where the universe handed Earth its script, and Earth immediately tore it up, set it on fire, and improvised something entirely new. This is the opening chapter of a world that would eventually host oceans, continents, and creatures capable of asking big questions about their origins. And it all begins in a time so mysterious that studying it feels like reading the prologue of a book that mostly burned away. Welcome to the Hadean, the era that shaped everything, remembered nothing, and left scientists enthusiastically sifting through cosmic crumbs. Picture Earth at this stage not as a planet, but as a glowing, restless cauldron doing its best impression of a cosmic lava lamp that got its settings stuck on maximum. The very idea of solid ground is laughable here. If you touch the surface, which to be clear you absolutely should not, you would sink through it the way a spoon disappears into hot soup. Earth was not yet a place where you could stand. It was barely a place you could point to without it looking back and hissing molten plasma at you like an annoyed cat made entirely of magma. This molten state was not some temporary tantrum. It was the default mood of young Earth. The heat came from everywhere at once. The leftover energy from planetary formation, the gravitational squeezing that occurred as heavy materials sank to the center, and the radioactive decay of elements that behaved like tiny internal furnaces. If early Earth had a personality, it was that friend who cannot sit still, keeps rearranging the furniture, and accidentally lights something on fire every 5 minutes. Nothing stayed where it started. Heavy metals plunged downward, lighter materials floated upward, and the entire globe churned like a simmering stew trying to mix itself into something stable. Adding to this dramatic performance, space debris had absolutely no intention of giving Earth time to breathe. In the early solar system, objects zipped around like cosmic bumper cars, except these cars exploded on impact and left craters the size of small countries. Earth was struck over and over, each collision releasing unimaginable heat, splashing molten rock across the surface, and occasionally blasting chunks back into space. If Earth had a smartphone, the number of notifications labeled incoming impact would have drained its battery instantly. The planet was in a constant state of renovation, except instead of construction crews, it had asteroids arriving uninvited and performing aggressive remodeling with the enthusiasm of caffeinated demolition experts. These impacts did more than just make Earth look like it lived in a bad neighborhood. They reshaped the planet's outer layers faster than you could say geological stability, Every time a large object slammed into the planet, it stirred the magma ocean and remelted sections that had only just begun thinking about solidifying. The result was a world trapped in an endless loop of almost there moments, like a cake that refuses to bake no matter how long it stays in the oven. You could practically imagine Earth shouting, "Can I please cool down for 5 minutes?" while yet another space rock answered, "Nope, incoming." Even below the surface, chaos ruled as materials sorted themselves by density. Earth's internal layers began to take shape, but they did so through a process that looked less like graceful separation and more like a geological food fight. Metal droplets rained downward in fiery storms toward the forming core, while pockets of lighter silicates surged upward. The entire interior behaved like a lava whirlpool with no off switch. Temperatures soared to levels that would make modern volcanoes feel underdressed. This internal churning created dynamic flows, heat currents, and chemical reactions that set the stage for everything Earth would eventually become, though at the time it was far too busy bubbling to appreciate the long-term consequences. Above all this, the sky, or whatever attempted to pass as a sky, was more like a shimmering haze of vaporized rock and metal. Vaporized rock. Imagine the air containing ingredients you would normally find inside a furnace, except the furnace itself is also the ground, the horizon, and the planet. Early Earth breathed out clouds of superheated material that cooled and condensed only to fall back into the magma like sizzling raindrops made of minerals. If weather forecasts had existed, they would have said things like, chance of molten drizzle increasing by afternoon, and visibility low due to atmospheric rock vapor again. Yet for all its hostility, there is something strangely admirable about this phase of Earth's life. This was the planet's raw, unfiltered energy on display, a kind of cosmic adolescence where everything is intense, dramatic, and constantly changing. The molten surface glowed with deep oranges and reds. The entire landscape shifted in waves, and rivers of liquid stone carved temporary paths before being swallowed by new eruptions. Even the cracks in the surface glowed like veins of fire, marking the restless pulse of a world still trying to figure out what shape it wanted to be. What makes this era even more fascinating is that the planet was not simply melting, it was learning. Every surge of magma, every reshuffling of elements, and every violent collision laid groundwork for the stable structures that would eventually emerge. Earth was, in its own destructive way, organizing itself. Out of this fiery chaos, patterns formed, layers differentiated. The core grew denser, the mantle churned with purpose, and the earliest hints of a crust tried to assemble themselves like a puzzle made entirely of hot, slippery pieces. And through all of this, Earth radiated heat like a cosmic lantern. From orbit, it would have looked like a glowing ember drifting through space, flickering with eruptions and illuminated by streaks of molten rock. There was nothing subtle about it. This was a planet making a loud entrance into existence, and subtlety was not on the menu. This was Earth before oceans, before continents, before gentler climates and peaceful blue skies. A molten sphere with a temper, powered by radioactive decay and constantly bombarded by the universe's own version of heavy artillery. It was chaotic, dazzling, violent, and absolutely essential. Because without this overheated phase, the planet would never have become the complex, layered world capable of supporting everything from raindrops to ecosystems to curious humans asking what it was like in the beginning. In this chapter of Earth's story, everything is molten, everything is moving, and everything is loud. The planet is not yet a home, but it is becoming one fiery churn at a time. Imagine Earth minding its own business, well, as much as a molten, fiery world can mind its business, when a planetary body roughly the size of Mars barrels in like it missed every turn signal in the solar system. Scientists call this intruder Theia, but given the circumstances, Earth might have preferred to call it absolutely not. This colossal collision was not a gentle nudge or even a rude cosmic shove. It was the kind of blow that rewrites destinies, a hit so dramatic that future planets probably whispered, "Did you see that?" from across the primordial neighborhood. Before the impact, Earth had finally begun developing a sense of direction. Its layers were differentiating. Its surface, though molten, was at least trying to behave consistently, and its orbit around the sun had settled into a respectable routine. And then, without warning, here comes Theia at full speed. There was no time to negotiate, no opportunity for conflict mediation, and definitely no, "Hey, maybe we can talk this out over volcanic coffee." Instead, there was a blinding flash of energy as two worlds collided with the force of a cosmic battering ram. When Theia struck, the impact zone would have lit up like a star deciding to audition for a brighter role. Molten rock erupted into space, shock waves rippled through Earth's interior, and debris blasted outward in a spectacular plume that wrapped the planet in a halo of glowing rubble. If there had been a narrator present, they would have paused dramatically and whispered, "And this is where things get interesting," while ducking behind a heat shield. The collision did not merely dent Earth, it reshaped it from the inside out. The crust and mantle were torn open like the rind of a fruit struck by a hammer. Portions of Earth were vaporized instantly. Chunks of Theia were obliterated into clouds of incandescent droplets. For a moment, Earth became a swirling, incandescent wound, a wounded titan in the darkness of space, glowing hotter and brighter from the sudden injection of unimaginable energy. The entire planet trembled, churned, and roared, not with sound, but with the violent shifting of molten rock trying to find new equilibrium. But here is the visionary part. Out of this catastrophe came one of Earth's greatest assets. The debris from the collision did not simply scatter and drift off into space. Much of it formed a disk of molten and vaporized rock orbiting Earth, a fiery ring that looked like Earth had spontaneously decided to cosplay as Saturn, just with far worse anger management. Within this ring, gravity rolled up its sleeves and got to work. Bits of debris clumped together, merging and growing, slowly building into a newborn moon. It is incredible to imagine that our serene, familiar moon began as a chaotic cloud of glowing shards, each piece a memory of two worlds that collided catastrophically. Over time, these fragments cooled, fused, and rounded off into the companion we recognize today. What started as a disaster turned into a stabilizing force that would influence tides, balance Earth's wobble, and eventually guide nocturnal creatures who had no idea their entire evolutionary trajectory hinged on an ancient planetary crash. Yet Earth's role in this cosmic drama did not end with providing raw materials for moon-making. The collision fundamentally changed Earth's personality. The impact altered its tilt, setting the stage for seasons that would shape climates and ecosystems millions of years later. It accelerated Earth's rotation, giving the planet shorter days than it would otherwise have had. Essentially, Earth came out of this cataclysm with a new orientation, a new rhythm, and an unexpected long-term partner orbiting overhead. If Earth had a therapist, they might say, yes, the event was traumatic, but look how much structure you gained afterward. In the immediate aftermath, however, structure was the least of Earth's concerns. The surface was once again a shifting sea of molten rock, far hotter than before. Rivers of glowing material raced across the planet. Tectonic foundations were rearranged, and the air filled with vaporized minerals that glinted like metallic ghosts. The sky glowed with the light of cooling debris, sparkling as fragments of Theia passed overhead, making early Earth look like it was hosting the universe's most dangerous fireworks show. Inside Earth, the impact stirred the molten interior into renewed motion. Metals sank more efficiently toward the core, strengthening the magnetic dynamo that would one day shield life from solar assault. Silicates redistributed throughout the mantle, creating new convection patterns that would influence geological behavior for eons. Earth was thrown into turmoil, but it was a kind of turmoil that forged structure in the long run. The planet was being reforged not just on the outside, but from its deepest layers outward. Theia itself became part of Earth's story in a very literal sense. Some of its materials sank into Earth's interior, becoming part of the planet's deep mantle. Some helped build the moon. Some vaporized completely, never to be seen again except in the faint isotopic fingerprints that scientists detect billions of years later. It is as though the two planets merged their histories into one complicated, molten autobiography. As Earth cooled from the collision, a long process that felt like the aftermath of an intense workout conducted inside a volcano, the planet began to stabilize once more. The moon, meanwhile, circled overhead, slowly pulling itself into a graceful orbit. For Earth, it was the cosmic equivalent of being hit by a truck, waking up, and discovering you had accidentally adopted a child, made of the truck's spare parts. But in a strange way, this was a turning point. The collision was catastrophic, yes, but it was also transformative. Earth gained a moon, a tilt, a faster spin, and a more organized internal structure. The chaos carved a new path forward. It was, in the end, the ultimate character-building moment, because sometimes the universe slams planets together not out of spite, but because the story needs a twist, and Earth, still glowing from the impact, would never be the same again. If Earth thought the moon-forming collision was the grand finale of cosmic chaos, The universe quickly corrected that assumption. Several 100 million years later, the solar system seemed to collectively decide that Earth had not experienced nearly enough unsolicited geological drama. Enter the Late Heavy Bombardment, a period when space rocks of all sizes lined up like a very determined meteor parade and took turns transforming Earth's surface into a patchwork of craters, molten scars, and geological bruises. If planets had Yelp reviews, Earth's comment section during this era would have simply read, "Would not recommend, keeps getting hit by strangers." To understand why this bombardment happened, we have to imagine a young solar system filled with wandering debris, asteroids, comets, and leftover formation fragments drifting around like cosmic clutter. The giant planets, especially Jupiter and Saturn, were adjusting their orbits in a gravitational dance that was beautiful in theory, but absolute havoc in practice. Their shifting tug on the asteroid belt destabilized countless chunks of rock, flinging them inward like nature's own malfunctioning pitching machine. Earth, still glowing faintly from its previous catastrophes, suddenly found itself in the wrong place at the wrong time, repeatedly. Each impact came with enough force to rearrange landscapes, vaporize rock, and excavate craters so deep they would make modern canyons look like timid scratches. Some of these objects were the size of mountains. Others were only as large as houses, but still managed to arrive with enough speed to make an over-caffeinated thunderstorm look gentle. A single strike could melt miles of crust, release plumes of superheated material, and punch temporary windows through the atmosphere. The surface of Earth was constantly being reset, smoothed, cracked, darkened, brightened, or simply erased. It was less like geology and more like someone kept hitting the refresh world button before the planet had time to save its progress. And yet, somehow, Earth took each hit and kept spinning. If the moon-forming collision was a defining blow, the Late Heavy Bombardment was the era that tested Earth's endurance. Every strike reshaped the surface in ways that scientists can only imagine, because almost none of the evidence remains. Later plate activity recycled most of the crust from this time period, swallowing ancient scars into the mantle like a cosmic house cleaner tasked with erasing every sign of the mess. It is as if Earth wanted to forget this era so badly that it buried the geological receipts under millions of years of new crust, magma flows, and tectonic rearrangements. What makes this bombardment so tantalizing for scientists is precisely that absence. On the moon, those scars remain. The surface is a gallery of ancient craters that serve as eyewitness testimony to the chaos Earth also endured. But Earth, being far more active and fond of constant remodeling, kept tidying itself up. The moon, in contrast, simply sat there gathering craters like stamps in a very destructive passport. So researchers look to lunar geology to reconstruct what Earth went through, comparing impact layers, crater densities, and melt signatures in a kind of interplanetary detective game. The clues whisper of a time when Earth's surface was under relentless siege. Back on Earth, Each impact would have sent tremors through the entire planet. Oceans did not yet dominate the landscape, and whatever water existed likely flashed into steam whenever a sufficiently large rock arrived. The atmosphere thickened with dust and vaporized minerals, darkening the sky and casting temporary shadows over a world still trying to stabilize its temperature. Some impacts unleashed enough heat to create vast lakes of molten rock, basins of glowing liquid that slowly cooled into new crust, each one covering up whatever came before. In a strange way, the Late Heavy Bombardment was both destructive and creative. It erased, but it also sculpted. Imagine looking at Earth from above during this time. You would see strikes flashing across the surface like cosmic lightning, each explosion briefly outshining the surrounding landscape. The glow of molten rock would illuminate the darkness, and plumes of ejecta would rise above the horizon in dramatic arcs. If Earth had a soundtrack then, it would have been mostly percussion, featuring impacts, eruptions, and the persistent rumble of a crust that never got a moment's rest. It was violent, yes, but also mesmerizing, like watching a world being hammered into its future shape. One of the biggest questions this era raises is what, if anything, managed to endure through it. Scientists debate whether any early crust, minerals, or chemical signatures survived the constant onslaught. Some propose that certain deep-buried materials might have escaped total destruction, preserved far below the surface where impacts could not reach them. Others argue that the bombardment may have sterilized the planet multiple times, resetting whatever fragile chemistry was trying to get a foothold. The truth is elusive, partly because Earth erased so much of the evidence, and partly because the bombardment itself was unpredictable. Some regions may have been battered relentlessly, others may have escaped with comparatively fewer craters. Earth was massive enough that no two regions experienced identical fates. But even without direct geological leftovers, the bombardment shaped Earth in lasting ways. It helped fracture the crust, creating weaknesses that would influence early tectonic behavior. It redistributed heat unevenly, stirring deeper layers and encouraging chemical mixing that would matter millions of years later. It may have delivered materials, from metals to volatile compounds, that contributed to Earth's evolving chemistry. The bombardment was like a prolonged, chaotic workshop where the planet was broken apart, reforged, and supplied with new tools all at once. Through it all, Earth endured like a heavyweight boxer who keeps getting knocked flat, but stubbornly stands back up. The Late Heavy Bombardment did not define Earth's end. It defined Earth's resilience. By surviving this era of cosmic target practice, the planet proved it could weather extremes that would have pulverized lesser worlds. And though scientists cannot directly read the story from Earth's rocks, the scars on the moon and the chemistry of meteorites allow us to reconstruct the echoes of that violent chapter. This was Earth during the bombardment, cratered, scorched, shaken, but unbroken. The planet emerged from that cosmic hailstorm more complex than before, carrying within its molten depths the memory of impacts that shaped the path ahead. Imagine Earth deciding it is finally time to cool off. After all the collisions, bombardments, and volcanic temper tantrums, the planet seems ready to settle into something resembling stability. But ready does not mean successful, because Earth's early cooling attempts were about as consistent as a malfunctioning oven that cannot decide if it is baking cookies or forging swords. The first crust that formed on Earth was not the sturdy, confident ground we stand on today. It was more like a thin, hesitant skin stretched over a seething interior, cracking at the slightest provocation and melting again whenever the planet so much as sneezed. Earth's surface at this time hovered in a delicate balance between cooling and chaos. On the outside, the temperature dipped enough for minerals to begin solidifying, forming patches of crust that temporarily cloaked the molten interior. These early crustal fragments were brittle and unstable, floating on the magma like fragile rafts made of mineral frosting. If you had stood on one, which for your own safety I must strongly advise against, you would have felt the ground tremble constantly under your feet. These first rocks were not landscapes. They were fleeting geological experiments that often ended in spectacular failure. Deep below, the mantle churned relentlessly, a cauldron of heat and motion that refused to calm down. Convection currents surged upward, carrying pockets of magma that behaved like overeager bakers, repeatedly opening the oven door too early. Every time the crust managed to thicken even slightly, hot material rose beneath it, weakening its structure until it cracked, collapsed, or dissolved back into the molten sea. Imagine the planet trying to bake a crust while the insides keep bubbling up like an overexcited pot of chili that refuses to stay contained. The cooling process was not uniform either. Some regions shed heat faster, solidifying into rocky plates that drifted atop the mantle like slow-motion icebergs. Other regions clung to their heat, boiling back into liquid whenever they attempted to harden. The result was a patchwork world where stability and instability lived awkwardly side by side. Here and there, small islands of crust might have lingered for a time, days, years, maybe longer, before being swallowed again by rising magma or shattered by internal pressures. If you could have mapped Earth's surface then, it would have looked like a jigsaw puzzle constantly being assembled and dissolved at the same time. And every attempt at cooling carried consequences for the atmosphere above. As the crust formed, gases trapped within the molten interior tried to escape, seeping upward in volcanic plumes that burst through weak spots like steam hissing from a kettle. These outgassing events added layers of vapor to the sky: water vapor, carbon compounds, sulfurous fumes, and a bouquet of other ingredients that would have made early Earth air smell like an industrial accident trying to pass as weather. But the atmosphere was still a chaotic haze, not yet ready to cool Earth efficiently. Heat leaked into space, yes, but slowly, painfully slowly, because the sky itself was too thick with lingering warmth and volcanic emotion. As cooling continued, Earth began experimenting with different crustal styles. Sometimes it would form smooth sheets of basaltic rock, only for them to fracture into jagged shards. At other times, it would push up thicker, buoyant sections that hovered briefly before collapsing. These variations were not signs of geological finesse. They were signs of a planet making things up as it went along, learning through repeated fiery trial and error. The crust was a temporary visitor in a land ruled by heat, and it never stayed long enough to become comfortable. This endless cycle of forming and erasing crust left behind almost no permanent record. Imagine writing a diary in pencil on a piece of paper, then setting that paper on fire every evening and starting over the next morning. That was Earth's geology at the time. Pages written and burned again and again, because each new crust wiped the slate clean, melted into oblivion, or was plastered over by fresh lava flows. Scientists today are left with precious few clues about what the earliest surfaces looked like. The planet essentially kept hitting the reset button before any long-term evidence could settle in. The frustratingly efficient nature of this self-erasure is why scientists struggle to reconstruct the details of Earth's earliest crust. Modern continents tell stories, but those stories begin long after this era ended. The minerals that survived from this time, rare, microscopic, often found deeply embedded in much younger rocks, are like lone survivors of a documentary that otherwise burned to ash. These tiny crystals whisper of conditions far different from anything we see today, but they cannot show the full picture. Too much was melted, recycled, or reburied before it ever had a chance to solidify into lasting history. But even in the midst of this geological chaos, something important was happening. Earth was learning how to behave like a mature planet. Each failed crust provided feedback. Each meltdown redistributed heat. Each temporary solidification allowed the mantle to release energy in new ways. Over time, these cycles gradually decreased in intensity. The planet's internal heat lessened, its outbursts became slightly less dramatic, and its crust became ever so slightly more capable of holding itself together. This was the slow, messy adolescence of a world struggling to cool off. There were no continents yet, no oceans, no steady rhythms in climate or geology. Only a planet stubbornly trying to harden a surface while its molten interior protested loudly. It was a process filled with drama and missteps, but also one that laid the groundwork for the more stable layers that would eventually cradle oceans, atmosphere, and life itself. Earth's first attempts at cooling were not graceful. They were clumsy, fiery, and repeatedly undone, but they were also essential. Through all the melting and reforming, the planet slowly learned to keep its crust intact, to regulate its heat, and to create the solid foundation on which the next chapters of its story would unfold. And beneath every modern landscape, every mountain, every grain of sand, there is the faint memory of those first fragile crusts, brief, flickering moments when Earth briefly pretended to be calm before melting itself again. If Earth had a to-do list in its earliest days, somewhere between stop getting hit by space debris and figure out what a crust is supposed to look like, there would have been a desperate scribble that read, "Cool down enough to make water stay put." Because for a long time, this planet was basically a sauna with identity issues. Far too hot for oceans, too steamy for comfort, and entirely too dramatic to let anything as calm as liquid water exist on its surface. But the universe loves persistence, and Earth, despite all odds, began its long, shimmering journey toward becoming a world with oceans. The first whispers of water likely rose from within the planet itself. Deep below the unstable crust, molten minerals held trapped ingredients, hydrogen, oxygen, and volatile compounds, waiting for their cue to escape. As Earth outgassed, volcanic plumes belched enormous clouds of steam into the atmosphere. Imagine a world where volcanoes were not occasional events, but everyday features, like nature's own collection of over-enthusiastic tea kettles. Each eruption pumped more water vapor upward, thickening the sky with a haze that must have made the planet look like it was forever caught in some grand cosmic exhale. This steam gathered in the atmosphere, circling the planet in dense, swirling currents. For ages, it refused to condense. The surface below was too hot, the air too thick, the crust too unstable. Rain wanted to fall, but every droplet evaporated before it even had time to brag about being a raindrop. The world simmered under a blanket of vapor, holding the promise of oceans the way a recipe book holds the promise of a cake. Not quite real, not quite ready, but tantalizingly possible. But volcanic outgassing was not the only delivery system auditioning for the role of Earth's water supplier. Far across the solar system, icy wanderers roamed, comets. These frozen travelers, filled with water ice, organic molecules, and the occasional dash of cosmic mischief, had been drifting for millions of years. Some of them began wandering close to Earth's orbit, nudged by gravitational currents, or simply swept into the wrong neighborhood. As they approached, Earth's gravity pulled them in, and they arrived in brilliant flashes of vaporizing ice and dust. Each impact delivered a small but meaningful splash of water, fleeting in the moment, but enormously important when multiplied by thousands of such encounters. If volcanic outgassing was Earth's internal faucet, comets were the universe's door-to-door water delivery service. The planet may have been too hot to keep liquid water at first, but it was slowly stockpiling. Water vapor thickened the air, icy fragments added more with every fiery arrival. The atmosphere swelled into a heavy, moisture-rich envelope that might have wrapped Earth in perpetual fog, the way a steamed-up bathroom mirror refuses to clear after a long shower. And then, slowly, Earth began to cool more effectively. The crust grew sturdier. The upper atmosphere lost some of its scorching heat to space. The blanket of vapor started to relax. At last, the temperature dipped low enough that water vapor could condense without instantly vanishing, a milestone equivalent to Earth saying, "I would like to stop being a cosmic sauna now, thank you." When the rain finally fell, it did not fall gently. It fell in torrents, sheets, and global downpours that may have lasted for thousands of years. Imagine endless storms sweeping across the surface, soaking the cooling crust, pooling in low regions that had never known stillness before. Lightning flashed, steam rose where hot rocks met cold droplets, and the ground hissed and cracked in response. This was not peaceful rain. It was planetary renovation through meteorological persistence. Gradually, these rains collected into vast basins, carving the earliest outlines of what would one day become oceans. The water spread, merged, deepened, and grew heavy enough to press down on the crust beneath it. Earth's surface, once a chaotic landscape of molten flows and fractured rock, transformed into something almost serene. The planet gained its first glimmers of blue, pale, shimmering, unstable, but undeniably beautiful. The earliest oceans were far from the tranquil waters we know today. They simmered with dissolved minerals, churned with volcanic heat from below, and swirled through landscapes still adjusting to being solid. Hydrothermal vents spewed minerals into the depths. Volcanic islands briefly pierced the surface before collapsing into the waves. These waters were not yet the cradle of life, but they were the cradle of possibility. In their roiling depths, chemistry danced more freely, temperature gradients formed, and the planet finally had a stable environment capable of nurturing complexity. Meanwhile, the sky above these oceans changed character entirely. The thick steam that once suffocated the horizon began to thin into a humid but breathable atmosphere. Sunlight started filtering through, reflecting off water in dazzling ripples, warming some areas and cooling others. Earth, for the first time, had weather patterns that involved actual clouds instead of just volcanic exhaust. The planet had crossed a threshold. It was no longer merely cooling, it was evolving. And this transformation did more than reshape the landscape. It altered the entire personality of the planet. Oceans moderate temperature. They store energy. They influence pressure, storms, climate, and the movement of air. Once Earth had oceans, it finally possessed the tools needed to calm itself. The chaotic tantrums of its youth gave way to rhythms, cycles, and patterns that could persist across generations of rock. But perhaps the most poetic part of this chapter is that Earth's oceans were born from both internal fire and cosmic ice. They were not a singular gift, but a collaboration, a blending of the planet's own outgassed breath with the frozen offerings of wandering comets. In a way, Earth built its oceans the same way we assemble something complicated today, part from internal resources, part from delivery. The earliest oceans were a declaration that Earth was ready for the next stage. The planet had cooled enough to hold water, stabilized enough to keep it, and transformed enough to begin shaping a world that could one day cradle life. For the first time, Earth wasn't a blazing sphere or a constantly melting crust. It was a world with waves, a world with storms, a world learning the art of calm. If you could look up at the sky during the Hadean era, assuming you somehow survived the boiling ocean's molten crust and general ambience of planets still under construction, you would not see the crisp blue canopy that modern Earth likes to show off. Instead, you would witness a sky so overloaded with volcanic gases and thick atmospheric haze that sunlight had to apply for permission just to peek through. Early Earth wore a constant veil, a smothering shroud of vapor and particulates that made the planet look like it was hosting an endless, over-the-top audition for most dramatic atmosphere in the solar system. The moment Earth began releasing gases from its molten interior, the atmosphere transformed from a thin wisp into a dense cloak. Volcanic vents and fissures were everywhere, acting like a planetary chorus of chimneys. They belched clouds of steam, carbon compounds, sulfurous fumes, nitrogen-rich vapors, and all kinds of gases that would make a modern-day air quality meter collapse in defeat. These emissions drifted upward, layer upon layer, until the sky became a swirling mix of chemical cocktails that would have felt more like inhaling a laboratory experiment than fresh air. Sunlight, poor thing, had no chance. Every beam entering this atmospheric labyrinth was scattered, absorbed, reflected, or bullied into dimming. The sky glowed with a murky luminosity, a shadowy illumination that made the world look like it was permanently stuck at the mysteriously ominous part of a movie. Even at midday, the light would feel more like an afterthought, diffuse, tinted, filtered through enough haze to make everything appear dreamlike and slightly threatening. If you were an ancient photon trying to reach Earth's surface, you would likely give up halfway and complain loudly to your supervisor. The volcanic gases themselves created shifting layers of atmosphere that behaved like mood swings. Some gases rose high and lingered, forming upper layers that trapped heat. Others clung close to the ground, thickening the air into an almost tangible presence. The result was a stratified blanket that changed color and density depending on the mix of eruptions in progress. One moment the sky might glow a deep reddish hue from iron-rich particles. The next it might fade into yellowish clouds driven by sulfur compounds. The whole scene would make a modern sunset look like a polite whisper by comparison. And then there was the fog, the dramatic, all-encompassing fog that gives this chapter its mood. This was not gentle morning mist. This was fog with ambition, thick, persistent curtains of moisture and particulates drifted across the landscape, fed by volcanic steam and atmospheric cooling. The fog rolled, pooled, and clung to everything, turning the horizon into a blurry suggestion and the air into a swirling, unpredictable stage. Imagine living inside a cloud that is constantly trying to reinvent itself artistically. The sky during this era was not just visually intense, it was active in every sense. Chemical reactions unfolded within the atmosphere as sunlight struggled to penetrate, sparking transformations that altered gas composition over time. Lightning flickered often, electrical discharges slicing through the haze, illuminating the fog banks with sharp, brief flashes. These storms were not trivial. They were powerful, widespread events, shaped by temperature differences and swirling vapors. An observer would have witnessed bolts of light tearing across the sky like cosmic highlighters refusing to be ignored. The atmosphere also trapped heat efficiently, making the surface below feel like it lived under an oppressive thermal lid. Heat radiating upward had to fight its way through multiple layers of insulating gases before escaping into space. Much of it lost the battle. This greenhouse-like effect kept Earth warmer than it otherwise would have been, contributing to the simmering environmental conditions that defined the Hadean world. The sky was not merely scenery. It was an active participant in Earth's climate struggles. a kind of atmospheric bouncer refusing to let heat leave without a confrontation. Yet despite its heaviness, the Hadean atmosphere had its own sort of beauty. There was grandeur in the swirling mists, the glowing clouds, the storms that lit up the haze like fireworks trapped inside a fog machine. There was an eerie elegance to the way volcanic plumes curled upward, merging with the sky until you could not tell where Earth ended and atmosphere began. Even the darkness had texture, a layered richness shaped by the interplay of gas, light, and heat. One of the most fascinating parts of this ancient sky is how little of it remains in any direct form. Unlike crust or minerals, an atmosphere does not leave behind fossils or rocks to tell its story. Scientists must infer its character from chemical traces locked in ancient crystals, or from simulations that piece together how gases from molten rock behave under extreme temperatures. The atmosphere of the Hadean era is the ultimate vanished witness, present for every transformation, yet leaving behind only whispers in the chemistry of minerals and the occasional isotopic clue. This atmospheric mystery only adds to its allure. The sky of early Earth is a ghostly chapter of planetary evolution, profound, essential, and impossible to fully recover. And in that mystery lies a certain poetic truth. The sky shaped what the planet became. It moderated temperature, shielded Earth from certain types of radiation, influenced surface chemistry, and helped orchestrate the conditions that preceded life itself. The dramatic fog was not just visual ambience, it was the engine of environmental change. Imagine standing beneath that sky, dense, glowing, unpredictable, and realizing that beneath all the haze and heat, something extraordinary was taking shape. Earth was not just cooling, it was maturing, evolving a sky that would one day clear, brighten, and make room for blue horizons and gentle sunsets. But in the Hadean era, the sky was a character all its own, moody, theatrical, and unapologetically intense. It wrapped the young planet in vapor and shadow, filtering sunlight through a veil of volcanic breath and setting the stage for a transformation that would take millions of years to unfold. Earth, at this moment in time, lived beneath a sky that refused to be ignored, a sky determined to make its entrance long before life ever looked up to admire it. If the Hadean era had a secret-keeping policy, it was an extremely effective one. Almost every surface, rock, and geological clue that might have described Earth's earliest days was melted, crushed, recycled, or simply obliterated. It was as though the planet had a strict rule against leaving evidence, an ongoing campaign to ensure that no curious future species could easily reconstruct what happened during its fiery youth. But fortunately for us, Earth did not clean up everything. Hidden within younger rocks, tucked away like misplaced treasures, there exist tiny crystals, zircons, that refuse to be erased. They are the stubborn archivists of the planet's earliest story, the microscopic historians quietly whispering, "Actually, I remember how things were." Zircons are not glamorous at first glance. They are small, unassuming minerals, often no bigger than grains of sand. You would scoop them off a beach without noticing anything extraordinary. Yet within these crystals lie some of the oldest solid materials ever discovered on Earth. They are the survivors of heat, pressure, bombardments, eruptions, and billions of years of geological remodeling. While the planet erased nearly all its early memories, zircons clung to theirs with a determination that would impress even the most dedicated librarian. Their resilience comes from their structure. Zircon crystals form a lattice so strong and tightly bonded that it resists melting even under extreme heat. When they do eventually melt, they tend to incorporate new materials or grow in ways that leave behind clues about their previous lives, like geological palimpsests covered in faint writing from earlier chapters. Once formed, zircons are incredibly difficult to destroy. They endure conditions that would reduce most minerals to dust or molten anonymity. This makes them ideal time capsules for an era that otherwise left no written record. Inside a zircon crystal, atoms are arranged in patterns that can trap other elements, storing them like notes slipped into a locked box. Some of these elements, particularly uranium, undergo slow, predictable decay into lead over vast stretches of time. By measuring the ratios of uranium to lead inside a zircon, scientists can determine its age with exquisite precision. Zircons do not lie, they do not exaggerate, and they do not suffer from memory lapses. When a zircon says it has been around for over 4 billion years, it means it. These ancient crystals were not discovered sitting in untouched Hadean landscapes, because such landscapes no longer exist. Instead, scientists find zircons embedded within much younger rocks, as though the crystals were castaways trapped in later geological formations. They survived earlier destruction, endured being swept up into new melts, and rode out billions of years of tectonic commotion to eventually be uncovered by patient geologists wielding microscopes. That these zircons still exist at all is a testament to their sheer stubbornness. Earth may have tried to reset itself repeatedly, but zircons were the exceptions that slipped through the cracks. What makes these crystals so valuable is not just their age, but the chemical clues they contain. The trace elements trapped inside them reveal details about the environment in which they formed. Certain isotopes suggest that even during the Hadean era, water interacted with rocks at Earth's surface. Other signatures hint at temperatures far cooler than one might expect from a planet still recovering from global bombardment and molten instability. These findings paint a picture of early Earth that is far more nuanced than the old idea of a world made entirely of lava and chaos. Zircons suggest that pockets of stable crust existed earlier than expected, tiny regions where rock solidified long enough for crystals to form and survive. These were not continents as we know them. They were likely small, transient surfaces, appearing briefly before being swallowed back into the mantle. But the fact that they existed at all changes our understanding of how quickly Earth cooled and how soon certain geological processes began. Zircons are the rare voices saying, yes, there were calm moments, even if they were brief. Through these tiny minerals, scientists also learn about the chemistry of the early crust. Some zircons contain signatures of elements that require specific conditions to form, conditions suggesting that Earth's early surface may have been far more complex than a uniform sea of molten rock. The crystals hint at variations in temperature, pressure, and composition. suggesting the planet was experimenting with diversity long before continents appeared. The Hadean world was not a featureless inferno. It was a patchwork of extremes, and zircons preserve the proof. Their microscopic size also makes them uniquely suited to survival. A large rock gets pulverized in a collision. A zircon often slips through unharmed. A towering mountain is destroyed by erosion. Zircons riding within sediment simply move elsewhere. They are the quiet stowaways of geology, passing unnoticed through countless cycles of destruction and creation. When Earth reworked its crust again and again, zircons were the hitchhikers, simply going along for the ride. In a very real sense, zircons are the closest thing we have to eyewitnesses of the Hadean era. They do not give us full sentences or illustrations, but they provide crucial details, temperature clues, chemical signatures, isotopic ratios that scientists use to reconstruct a world otherwise lost to geological amnesia. Without them, we would be squinting into the void of Earth's earliest history with almost nothing to guide us. With them, we have tiny windows into a vanished world. Their survival is almost poetic. In an era defined by violence, melting, and relentless change, these crystals represent persistence. They remind us that even in the most turbulent times, some pieces of the past endure, and through those pieces, we glimpse landscapes no longer present, conditions no longer visible, and processes no longer active. Zircons, in their quiet tenacity, allow us to reach back through billions of years and touch the memory of a planet that seemed determined to forget. They are Earth's reluctant archivists, small, durable, and invaluable. If we could watch the Hadean Earth from a safe vantage point, ideally somewhere not in danger of melting, we would see a planet trying very hard to figure out the art of plate tectonics. Today, Earth moves its plates with confidence, vast slabs of crust sliding, colliding, and pulling apart in a geological ballet that shapes continents and oceans. But in its earliest days, those plates were more like nervous dancers wandering on stage before rehearsal, bumping into each other accidentally, missing their cues, and occasionally bursting into flames. Nothing about early tectonics was graceful, nothing was consistent, and nothing stayed in place long enough to declare itself a continent. The crust at this point was still experimenting with stability. After cycles of cooling, cracking, melting, and reforming, the planet had finally begun producing patches of crust thick enough to behave like embryonic tectonic plates. But these early fragments were fragile things, thin, easily heated, easily broken, and pushed around by a mantle that behaved like a simmering ocean of restless stone. The mantle's convection currents were vigorous, swirling with temperature contrasts far greater than anything modern Earth experiences. Imagine trying to balance a flat board on top of a washing machine set to the angriest spin cycle. That was early plate tectonics in a nutshell. As these proto-plates tried to drift, they often found themselves dragged downward into the hotter depths, melting away before they could establish any long-term arrangement. Subduction, the process where one plate slips beneath another, may have occurred, but awkwardly, inconsistently, like a clumsy dance partner who keeps stepping on their own feet. Some plates were too buoyant to sink fully. Others were so thin that they folded or cracked instead of diving. The mantle, meanwhile, surged upward in plumes that struck the base of these early plates with the enthusiasm of a boiling pot lifting its lid. The result was a landscape in constant rearrangement, where nothing could relax for more than a geological blink. If any land existed above the ocean surface, and evidence suggests only small, scattered bits might have, it would have been temporary. These early proto-continents were not the sturdy land masses we know today. They were fragile rafts of crust, thick enough to rise above water, but not thick enough to resist being swallowed back into the mantle. They might have formed short-lived islands, only to disappear in fiery episodes of subduction or break apart under the stress of rising magma. Imagine an archipelago made entirely of unstable platforms that occasionally sank without warning. That was Earth's first attempt at continental architecture. What drove these early movements was the same engine that powers tectonics today: heat. Earth's interior was much hotter than it is now, and that heat created immense pressure differences. Hot regions deep in the mantle rose toward the surface, spreading sideways beneath the crust before cooling and sinking again. This circular motion churned relentlessly, pushing and pulling the thin plates like a puppeteer who had not yet figured out the strings. But unlike modern plate tectonics, with its relatively orderly boundaries and recognizable patterns, Hadean tectonics was chaotic improvisation. Boundaries were short-lived, ridges formed and disappeared. Subduction zones initiated and then failed. The choreography changed every few million years, which in planetary time is barely an opening act. These dynamics had enormous consequences. As plates fractured and collided, they altered the chemistry of the crust. Some fragments grew thicker through repeated cycles of melting and resolidifying, beginning the slow evolution toward continental crust. Others dissolved into magma, contributing to the mantle's complexity. Early tectonics was not just motion. It was a chemical factory reshaping the planet's outer layers. In every crack, collision, and melt event, new minerals formed, old ones transformed, and the raw materials for future continents began to accumulate. Even if the performers were clumsy, the dance still achieved something monumental. The absence of long-lived continents during this time means that much of Earth's early surface history is lost to us. Anything the Hadean plates built was almost certainly destroyed. If a proto-continent did manage to stabilize briefly, it was likely recycled into the mantle long before it could leave behind recognizable rock. This relentless turnover is one reason why the Hadean era is such a geological mystery. Earth kept throwing out the script before any lines could be recorded. The world was editing itself aggressively, leaving only tiny mineral clues, not sweeping landscapes, to hint at what once existed. Still, scientists can infer the presence of early tectonic behavior through indirect evidence. Some ancient zircon crystals contain chemical signatures that suggest they formed in regions undergoing tectonic-style melting. These clues hint at rocks being pulled deep into the mantle, reheated and pushed back up again, exactly the kind of cycling that plate tectonics creates. Other mineral traces, hint at temperature variations linked to plate movement. Though we do not have the plates themselves, we have the fingerprints of the processes that shaped them. Imagining the surface at this time requires embracing a world in flux. Volcanoes dotted the landscape. Fissures opened and closed. Crustal fragments drifted toward each other, collided, buckled, and sometimes fused briefly before tearing apart again. The boundaries between plates would have glowed at night, lit by the constant volcanism driven by intense internal heat. The crust groaned, cracked, and reassembled over and over, like a puzzle being shaken before anyone had a chance to finish it. But through all the awkwardness, early tectonics was building towards something. Each failed subduction zone, each brief collision, each patch of thickened crust was practice, a step toward the stable tectonic engine that would one day form continents large enough to support ecosystems and oceans deep enough to moderate global climate. The planet was learning slowly, painfully, through countless geological missteps, how to move its outer shell without destroying it entirely. These early, shy tectonic performers may not have dazzled with their grace, but they set the foundation for everything that followed. The continents we stand on today, the mountains we admire, and even the deep ocean trenches owe their existence to the chaotic experiments of these first drifting plates. The Hadean Earth may not have been elegant, but it was persistent, and in the end, even the clumsiest choreography can lead to a masterpiece. Deep beneath the restless surface of the Hadean Earth, long before continents gathered their courage or oceans tamed their volatile tempers, the planet was busy constructing something extraordinary in the shadows. It was not building mountains yet, nor sculpting valleys, nor preparing any scenery fit for future organisms to stroll across. Instead, it was crafting laboratories, hidden, churning, ancient chemistry workshops nestled along the seams of the ocean floor. These were hydrothermal systems, and they were among the most dynamic, volatile, and oddly creative environments Earth had to offer. Imagine a landscape where seawater, still young and mineral-rich, seeped into cracks in the crust. As it traveled downward, the water encountered rock heated by a mantle that still behaved like a forge in full operation. Temperatures soared, minerals dissolved, recombined, and reacted in ways that would make modern chemists both delighted and mildly concerned. Then, superheated and transformed, the water burst back upward through vents, releasing torrents of chemical energy into the surrounding ocean. It was less like a gentle spring and more like a planet opening its internal oven and announcing, "Fresh reactions available. Come get them while they're hot." These vents were far from uniform. Some spewed dark, mineral-laden plumes that billowed like underwater smokestacks. Others released clear, superheated fluids rich in hydrogen and metals. Each type of vent offered a different chemical environment, like the planet was experimenting with a variety of recipes to see which combinations might produce something interesting. Pressures were immense. Temperatures swung wildly. Minerals precipitated into strange chimney-like structures that grew along the vents, forming walls and towers that looked like they belonged in a surrealist sculpture garden. This was Earth's first attempt at building architecture, and it did so accidentally. Within these churning systems, gradients were everything. Gradients of heat, of acidity, of chemical composition. Nature loves gradients because they are opportunities. A temperature difference here, a proton imbalance there, a sudden influx of dissolved metals. All these conditions set the stage for reactions that did not happen anywhere else on the planet. In the spaces between hot vent fluids and cooler seawater, complex molecules could begin forming. Carbon-based compounds met mineral surfaces that acted like catalysts, nudging atoms to assemble into shapes they had never tried before. Some of these molecules would break apart immediately, others would persist a little longer, and a very rare few might have combined in such a way that they gained a tiny advantage: stability, reactivity, or the ability to interact with other molecules in intriguing ways. To be clear, no single vent created life in a dramatic lightning strikes the primordial soup moment. The process was subtle and patient. It was chemistry meandering toward complexity, guided not by intention, but by opportunity. Every reaction was a roll of the cosmic dice, and the vents simply kept rolling. With each burst of mineral-rich water, each interaction with catalytic surfaces, each shift in temperature, the ocean gained a new set of experimental results. Some combinations were dead ends. Others may have quietly inched closer to the kind of stability and self-organization that life eventually required. These environments were also chaotic enough to encourage innovation. The mineral chimneys forming around the vents created cages, pores, and tiny chambers, natural test tubes where molecules could mingle, separate, recombine, or get trapped long enough to undergo transformations they would never experience in open water. These microspaces provided order within the chaos, offering just enough structure to allow chemical reactions to build upon each other. It is easy to imagine these chimneys as racks in Earth's earliest chemistry set, their porous walls guiding reactions the way a modern lab bench organizes glassware. And while the surrounding oceans were still adjusting to their new existence, these deep-sea vent systems persisted. They weathered changes in temperature, shifts in tectonic activity, and fluctuations in seawater chemistry. No matter what upheaval struck the surface world, the vents kept working, steady, tireless, and incredibly generous with their chemical output. They were not fragile environments. They were resilient, powered by the internal heat of the planet itself, and capable of continuing their experiments for millions of years without losing enthusiasm. It is in these very conditions, stability wrapped in chaos, structure mingled with turbulence, that many researchers see the potential beginnings of biological chemistry. Life, after all, is not just the presence of complex molecules. It is the ability of those molecules to organize, persist, and interact productively. And where better to begin such delicate negotiations than in an environment offering both shelter and energy? Hydrothermal vents provided chemical fuels, mineral scaffolds, protection from destructive ultraviolet radiation, and a constant supply of raw materials to play with. Perhaps the most compelling part of these systems is how naturally they generate the types of energy gradients life depends on today. Modern cells rely on differences in chemical potential to power their processes. They shuttle ions across membranes, harnessing those flows to perform work. In some hydrothermal vent systems, natural mineral structures created similar gradients long before the first membrane-bound cells existed. It is as if the planet accidentally built prototypes of cellular energy systems and left them running, waiting for molecules to take advantage. Whether or not life first emerged in these dark, mineral-rich environments, the influence of hydrothermal systems on early Earth cannot be overstated. They were reactors, inventors, and architects all at once. They mixed, heated, cooled, catalyzed, and reconfigured the ingredients available, offering endless permutations for chemical evolution to explore. Even if the very first self-replicating systems emerged elsewhere, vents almost certainly contributed pieces of the puzzle, molecules, pathways, or conditions that nudged the planet's chemistry closer to biology. In the dim glow of those ancient vents, beneath countless tons of restless ocean, Earth was whispering to itself. Its vents muttered in mineral dialects, encouraging molecules to interact, assemble, and reorganize. It was not a shout, not a dramatic moment, but a quiet suggestion repeated for millions of years. What if something formed that could stay? What if chemistry learned a trick or two that lasted beyond the next reaction, and though life had not yet appeared, the stage was now set. The chemistry had practiced, the ingredients had mingled, the vents had stirred the ocean thoroughly. When life finally did emerge, whenever and wherever that happened, it would inherit a world already rich with the tools it needed. The hydrothermal vents were not life's birthplace in any definitive sense, but they were Earth's earliest classrooms, steamy, turbulent, unpredictable classrooms, where molecules first learned how interesting they could become. Before life claimed any corner of Earth, before cells assembled membranes or proteins learned how to fold properly, there existed a strange experimental era when chemistry began stretching its legs toward biology without fully realizing where it was headed. This was prebiotic chemistry, a time when molecules behaved like actors in a rehearsal for a play that would not premiere for millions of years. They had no scripts, no direction, and certainly no understanding that their interactions would one day give rise to organisms debating their own origins. Yet little by little, these modest molecular players started flirting with complexity, drifting toward patterns that hinted at something more organized than mere reactions. At this stage, Earth offered a playground full of possibilities. Its oceans carried dissolved minerals, organic compounds, and volatile ingredients delivered by geological processes and wandering celestial visitors. The atmosphere crackled with energy from lightning and radiation, sending sparks of possibility into the chemical soup below. On the surface, pools and shorelines dried and refilled, concentrating molecules into accidental workshops where reactions occurred more readily. Everywhere on the planet, the chemistry was restless, curious, even, transforming simple molecules into slightly more elaborate versions of themselves through a combination of chance, energy, and natural affinity. The first step toward complexity likely involved the formation of organic molecules that were more than just basic carbon chains. These molecules might have arisen through atmospheric reactions ignited by electrical bursts or ultraviolet light, or they could have formed in mineral-rich environments where natural catalysts nudged atoms into new arrangements. Once present, these molecules drifted through Earth's young environments like singles at a cosmic mingling event, bumping into each other, sometimes reacting, sometimes ignoring each other, and occasionally stumbling into arrangements that lasted longer than expected. Among the earliest precursors to biological organization were molecules capable of sticking together in meaningful ways. Some may have formed clusters that behaved like primitive assemblies, capturing other molecules or creating small pockets of altered chemistry. These gatherings did not have purpose, of course. They simply existed because their shapes and charges allowed them to persist. Yet persistence is one of the first quiet victories on the long road to life. Anything that lingers has a chance to interact again, and interaction is the heart of prebiotic evolution. Energy was the matchmaker driving these encounters. Radiation, geothermal heat, and chemical gradients all provided nudges that pushed molecules into reactions they might not have attempted otherwise. Sometimes these reactions produced nothing special. Sometimes they produced compounds that quickly degraded, and sometimes, rarely but importantly, they produced something slightly more stable. Stability allowed repetition. Repetition allowed accumulation. And accumulation allowed chemistry to test new combinations simply by virtue of being in the right place for long enough. One of the most captivating ideas in prebiotic chemistry involves molecules that can assist in their own formation. These self-promoting reactions did not require intention or guidance. They simply took advantage of conditions that favored their repetition. A molecule might catalyze the creation of a copy, or at least an approximate relative, by helping other reactants align correctly. These catalytic tendencies were small, imperfect, and entirely accidental. Yet they introduced a new element into the chemical landscape, the possibility that some structures could persist across multiple cycles of formation and breakdown. As molecules gained more elaborate structures, they began to exhibit behaviors that hinted at rudimentary information storage. Certain sequences of atoms were more stable or more reactive than others, leading to chains or rings that could influence how new compounds formed nearby. These interactions were not genetics, not even close, but they represented the faint beginnings of systems where structure guided future chemistry. Imagine a world where shapes and charges served as the earliest forms of instruction, where the architecture of a molecule dictated how it could participate in the next round of reactions. Surfaces played a crucial supporting role in this unfolding drama. Minerals with charged surfaces provided footholds where molecules could align, concentrate, or react more effectively than they could in open water. They acted like the planet's first assembly lines, positioning ingredients close enough for chemistry to take advantage of the convenience. Some minerals encouraged long chains to form. Others promoted branching or ring formation. The result was a rich variety of molecular shapes, some of which possessed qualities that nudged them closer to the threshold between chemistry and biology. Over time, mixtures of molecules began interacting in increasingly complex ways. Some combinations created microenvironments that behaved differently from the surrounding water, tiny gatherings where reactions occurred more readily or where certain structures accumulated while others dispersed. These pockets were not cells. They had no walls, no boundaries, no metabolism, but they represented a step toward compartmentalization which would one day become essential for life. In these small accidental gatherings, chemistry could repeat itself with a bit more consistency, allowing rudimentary systems to persist longer than their isolated counterparts. Speculation in this field inevitably touches on the tantalizing idea of molecules that could copy themselves, even imperfectly. A structure capable of encouraging a similar structure to form would represent a monumental shift. It would blur the line between simple reaction and something approaching continuity. These early systems may have been sloppy, error-prone, and easily disrupted, but their existence, if they existed, would have marked one of the first whispers of life's arrival. And through all of this, Earth was not supervising or imposing direction. It simply provided a restless environment full of opportunities. Molecules tried things because the laws of physics allowed them to. Reactions occurred because conditions favored them. Structures persisted because they were stable enough to survive a little longer than their neighbors. In this slow and uncertain dance, chemistry groped its way toward complexity, piece by piece, step by step. Prebiotic chemistry did not announce itself with fanfare. It did not proclaim, "Life is coming." It moved quietly, experimentally, allowing countless combinations to form and dissolve across millions of years. But within that vast expanse of time, the planet nurtured patterns of interaction that gradually grew more robust. And somewhere in that sprawling landscape of possibilities, chemistry made a subtle but monumental shift. It stopped being just chemistry. It started becoming something that could one day call itself alive. Trying to reconstruct the Hadean era is a bit like trying to solve a mystery when most of the witnesses have vanished. The crime scene has been redecorated 17 times, and the only surviving clues are microscopic, cryptic, and annoyingly sarcastic about how little they reveal. Earth has always been a planet with dramatic flair, but during the Hadean, it also perfected its skill at erasing its own history. The evidence that would normally help geologists piece together an ancient world was systematically melted, crushed, recycled, or launched into the cosmic void with enough enthusiasm to make even the toughest rocks question their life choices. So when scientists attempt to peer back into that era, they are essentially reconstructing an epic saga from the geological equivalent of confetti. One of the biggest culprits behind this great planetary cover-up is the relentless recycling of the crust. Modern Earth still loves to swallow its own surface through subduction zones, but the Hadean version operated on a level of intensity that would make today's tectonic activity look like a leisurely shuffle. The early crust was thin, fragile, and constantly assaulted by internal heat. Whenever it formed, it was promptly torn apart, melted down, and mixed back into the mantle like ingredients in a cauldron that refused to stay separate. If rocks had dreams of longevity, the Hadean was where those dreams went to die. This endless recycling means that the planet's first surfaces barely lasted long enough to accumulate meaningful records. Any chemical signatures they held, any shapes they formed, any stories they might have whispered about Earth's earliest conditions were swallowed back inside and transformed beyond recognition. By the time the planet cooled enough to preserve long-lasting crust, millions of years of early history had already been wiped clean. It is as though Earth spent its infancy scribbling furiously on chalkboards and erased them every few minutes before anyone else could read the notes. Then there is the matter of impacts. The Hadean Earth did not merely experience collisions, it was hunted by them. Space rocks targeted the planet with the precision of cosmic pranksters determined to interrupt geological progress. Every large impact did its own version of renovation, excavating enormous craters, vaporizing materials, and blasting ejecta into space. Some chunks were lost forever, scattered into interplanetary orbits or fused into debris that drifted away. Other fragments rained back down in molten showers, creating layers of mixed, chaotic material that obscured whatever subtle geological patterns existed beforehand. Imagine baking a cake and then repeatedly dropping meteors into it. Good luck identifying the original recipe. Heat played its part too. The Hadean Earth radiated thermal energy like a small star impersonating a planet. Between radioactive decay, leftover formation heat, and the relentless churn of the mantle, temperatures remained high enough to obliterate delicate structures and erase chemical distinctions. Rocks that might have recorded early surface conditions were repeatedly heated past their melting points, scrambling their internal arrangements. Any minerals that survived did so not because the planet was gentle, but because those minerals possessed the stubbornness of heroes in an epic saga who refused to perish despite overwhelming odds. Even the atmosphere, thick with volcanic gases and swirling haze, contributed to the disappearance of evidence. Chemical reactions altered materials before they had a chance to settle into stable forms. Erosive processes, though primitive compared to later eras, still played a role in breaking down exposed surfaces. Water, once it finally pooled on Earth, triggered new kinds of chemical weathering that transformed rocks and carried dissolved components into the depths. In short, the planet treated evidence the way a mischievous pet treats important documents, with enthusiasm and zero regard for preservation. Complicating matters further, the few relics that did survive have been scattered across billions of years of geological reshuffling. To find them, scientists must sift through much younger rocks, searching for mineral grains that predate the host formations by vast stretches of time. These ancient fragments are rare, tiny, and often isolated. Using them to reconstruct the Hadean is like trying to infer the plot of a novel from a handful of letters cut out of the original pages. They offer glimpses, valuable, tantalizing glimpses, but they cannot provide a full picture. And yet, even these scraps of evidence would be more straightforward if not for the fact that Earth has spent its life moving, twisting, and transforming every inch of its surface. Plate movements bury rocks deep underground, where pressure and heat rewrite their mineral compositions. Later uplift exposes them again, only for erosion to gnaw at the edges. The result is a geological library where the shelves keep rearranging themselves. Half the books have been burned and rewritten multiple times, and the surviving chapters are missing key paragraphs. The Hadean section, unsurprisingly, is mostly blank. All of this makes proving anything about the Hadean era an exercise in scientific resilience. Researchers approach the problem with creativity, combining clues from geochemistry, simulations, astronomy, and mineral studies. They examine the isotopic signatures locked in ancient crystals, compare Earth's early evolution to that of other rocky bodies, and use physics to model how the planet might have behaved under conditions that no longer exist. The goal is not to recreate every detail, but to narrow the possibilities, to understand the broad strokes of a time when Earth was simultaneously too active to preserve its past and too young to realize how much that past would matter. What emerges from these efforts is a picture that feels simultaneously confident and speculative. We know the Hadean was hot. We know the crust was unstable. We know impacts were frequent and transformative. We know the atmosphere was thick and volatile, but the finer details, the shapes of the first surfaces, the pacing of cooling, the subtleties of chemical cycles, remain hidden, lost beneath billions of years of planetary revision. This difficulty is not a failure of science. It is a testament to Earth's wild youth. The planet did not merely experience change, it embodied change. Its earliest chapters were written in fire, overwritten in magma, edited by collisions, and redacted by erosion. And perhaps that is fitting. The Hadean era was not meant to be a peaceful archive. It was meant to be a forge, a crucible, a dramatic beginning. If proving anything about that time remains a challenge, it is only because Earth was too busy becoming a world to pause and keep good records. And honestly, for a planet learning how to exist, you can hardly blame it. If the Hadean era was Earth's chaotic childhood, full of fire, tantrums, and episodes where the planet accidentally launched parts of itself into space, then the transition into the Archean was the moment it finally took a deep breath and said, "All right, let's try being stable for once." The shift did not happen in a single dramatic flourish. There was no instant transformation where molten wastelands suddenly became a serene blue world. But over millions of years, Earth slowly traded its role as the solar system's most excitable troublemaker for something resembling a planet, prepared to document its own existence. The cinematic transition from the Hadean to the Archean is one of the greatest tonal shifts in planetary history, less an abrupt cut and more a gradual fade from blazing orange chaos to a world where solid ground stayed solid long enough to write stories into stone. Imagine the scene opening on an Earth still glowing faintly from the inside, its surface patched with new crust, forming in hesitant layers. Volcanic eruptions continue to punctuate the landscape, but they are no longer the constant barrage that defined earlier ages. The air remains heavy with steam, carbon compounds, and leftover heat. But for the first time, windows of clarity appear. Moments where sunlight cuts through the haze without immediately turning the sky into a blurry furnace glow. Oceans deepen, shorelines stabilize. The soundtrack shifts from explosive percussion to something more like a simmering hum. Earth has not found peace exactly, but it has found rhythm. This new rhythm marks the beginning of geological continuity, where Hadean crust resembled a series of drafts abandoned mid-sentence. The earliest Archean crust begins to hold its form. Rocks persist, minerals accumulate, layers survive long enough to record pressures, temperatures, and chemical interactions. For the first time in planetary history, Earth stops wiping the slate clean every few geological minutes. It begins keeping a diary, not a neatly organized one, but a diary nonetheless, written in the language of metamorphic textures, isotopic signatures, and the stubborn endurance of ancient minerals. The continents, or what will eventually qualify as continents, also begin their long and awkward formation process. Instead of transient crustal rafts that sink or melt before anyone can take attendance, the Archean sees the emergence of more resilient crust, patches thick enough to resist being swallowed every time the mantle shifts. These early continental blocks, called cratons, are small compared to modern landmasses, but they are mighty in their longevity. They form slowly, piece by piece, through cycles of partial melting, collision, and tectonic thickening. Over time, they become the immovable anchors of Earth's crust, the chapters in the diary that refuse to be edited out. But the transition from Hadean chaos to Archean clarity is not just about crust, it is also about temperature. Earth's interior cools enough that volcanic activity, while still vigorous, becomes less globally apocalyptic. The mantle stops overturning with the enthusiasm of boiling water, and instead circulates in more organized patterns. These changes give the crust a fighting chance. Magma still rises, but it does so in ways that allow some regions to survive the disruption. Lava still pours across the surface, but it is no longer guaranteed to erase everything beneath it. Heat is no longer the planet's enemy. It becomes a sculptor, refining rather than obliterating. Meanwhile, the oceans undergo their own transformation. They expand, deepen, and begin interacting with the crust in ways that promote new chemistry and mineral formation. Water seeps into cracks, alters rocks, and contributes to the growth of minerals we recognize today as signatures of stable, long-lived geological environments. As the oceans cycle across the forming crust, they carry dissolved materials that influence the atmosphere, the temperature, and the landscape. Earth is no longer merely cooling. It is negotiating equilibrium. Atmospheric changes add another layer to this cinematic shift. The dense veil of the Hadean thins just enough to let more sunlight reach the planet's surface, warming regions unevenly and encouraging early weather cycles that are slightly less dramatic than their predecessors. Storms persist, but they become part of a developing climate system rather than the chaotic outbursts of a world unsure how to regulate itself. The planet still sweats, boils, and vents, but it does so with the beginnings of pattern, the earliest hints of predictability. In this era of transition, the rocks that survive become storytellers. They record chemical traces of early oceans, hints of tectonic behavior, and evidence of a planet that no longer discarded its materials in fiery tantrums. Metamorphic rocks preserve pressure histories. Volcanic layers capture the timing of eruptions. Sediments begin to appear, settling quietly in basins long enough to matter. Each surviving stone is a page in Earth's first reliable journal, documenting experiences no older rock was able to articulate. These rocks reveal another intriguing development: the stirrings of biological potential. While life's earliest confirmed fossils appear later, the Archean holds chemical fingerprints that suggest the environment was becoming increasingly favorable for biological chemistry. Stable oceans, persistent land masses, and less destructive surface conditions all created new opportunities for molecules to organize and evolve. The planet was not yet alive, but it was beginning to hum with the environmental consistency life would need. The cinematic quality of this transition lies not in sudden spectacle, but in the slow emergence of order from chaos. A world that once flashed, boiled, cracked, collapsed, and reformed with reckless abandon now found the patience to let its surface linger. Where once the mantle devoured everything, it now allowed some creations to stand unbroken. Where sunlight once struggled to penetrate the atmospheric murk, it now streamed through in growing stability. The camera would pan across an Earth still rough around the edges, but undeniably on the cusp of something transformative, a planet learning how to endure rather than explode. By the time the Hadean fades into the Archean, Earth has become a place capable of preserving memory. Its diary may be incomplete, smudged, and occasionally charred around the edges, but it exists. It is readable, and it tells of a planet that survived its own temper long enough to begin keeping track of itself. The stage is built. The lights are dimming to something gentler, and in the shadows of this shift, Earth prepares for its next act, one where life will finally step into the frame. By the time we reach the end of Earth's Hadean saga, we are left with the strange feeling of having watched a movie where most of the scenes were deleted. Half the cast wore fireproof armor, and the script was improvised by a planet still figuring out which end was up. And yet, somehow, scientists have managed to reconstruct this near-forgotten era, an era that seemed almost determined to avoid being captured in the geological record. The Hadean is the ultimate reluctant storyteller, a period whose memories were melted, shattered, recycled, or blasted into space, but whose faintest whispers still echo through the materials that survived. And those whispers, as fragile as they are, have become the clues that bring the planet's origin story to life. The astonishing part is not just that scientists know anything about the Hadean, it is how they know it. Reconstructing this era requires detective work of a caliber that would make fictional investigators feel underqualified. There are no intact rock layers to examine. There are no landscapes frozen in time. There are not even fossils, not unless you count ancient mineral grains that function less like photographs and more like cryptic notes scribbled in the margins of a damaged book. But geologists, chemists, physicists, and planetary scientists approach these remnants with the determination of people trying to read a burned manuscript using only the remaining flecks of ash. Every scrap of evidence matters. Every grain tells a story, even if that story requires decades of teamwork to interpret. This reconstruction is possible because science thrives where mystery thrives. Instead of being discouraged by missing pages, scientists embrace the challenge, using creative tools to fill in the gaps. They examine the chemistry inside zircon crystals to infer temperatures and conditions from billions of years ago. They run simulations of massive impacts to understand how a collision could produce a moon. They compare Earth's early evolution to that of other rocky bodies, treating planets across the solar system as siblings with shared childhood experiences. They study meteorites for clues about the materials that built our world. Each line of evidence is a thread, and together those threads weave a tapestry that brings the Hadean into view, not completely, but vividly enough to imagine. And what a story emerges when those threads align. We see a world that began as a molten sphere, glowing with internal heat and struggling to hold itself together under the weight of constant impacts. We see oceans forming through a mix of volcanic outgassing and cosmic delivery. We see the atmosphere shifting from suffocating haze towards something more structured. We see the crust attempting to stabilize, wobbling through early tectonic experiments that hinted at the continental architecture to come. We see chemical reactions drifting toward complexity, rehearsing for life long before life stepped onto the stage. It is a messy, dramatic, and awe-inspiring story, one that feels almost too grand to fit into a mere chapter of Earth's history. But the beauty of this concluding moment lies not in the details alone, but in the realization that Earth's violent beginnings were essential. Without the heat, the collisions, the molten churn, and the atmospheric theatrics, Earth would never have achieved the conditions needed for its later transformation. Chaos was not just background noise. It was the engine that forged the world. Every melting episode reshaped the crust. Every impact stirred the mantle. Every cycle of cooling and heating redistributed materials in ways that ultimately allowed the planet to settle into the quieter rhythms of the Archean. The Hadean might not have kept a diary, but it left fingerprints on everything that followed. What makes the Hadean even more fascinating is how it reframes our understanding of Earth as a whole. We tend to think of planets as static objects, spheres that exist largely unchanged across time. But the Hadean shows us a planet in flux, a world capable of reinvention. Earth's identity was molded through extremes, sculpted by processes that pushed it to its limits. The scars of that era are gone, but the consequences are everywhere. The continents we walk on, the oceans that cradle life, the magnetic field that shields us, all of these things trace their origins back to a time when the planet behaved more like a cosmic furnace than a home. And perhaps the most magical part of this conclusion is the reminder that we, as thinking organisms, are capable of reaching back through billions of years to a time we can never witness. Through tools, logic, creativity, and an endless appetite for discovery, humanity has learned to listen to the faint echoes of a world that erased most of its tracks. The Hadean may not have wanted to be remembered, but we remember it anyway, because we insist on understanding where we come from. It is an act of curiosity, resilience, and trust in the idea that even the faintest evidence can illuminate an entire era. As we close this chapter, the Hadean becomes less a void in Earth's history and more a testament to the planet's remarkable journey. It reminds us that beginnings do not have to be tidy to be meaningful. They can be explosive, uncertain, and downright chaotic, yet still pave the way for something extraordinary. The fact that we can reconstruct even fragments of this era is a triumph of scientific imagination, a tribute to the persistence of researchers who chase whispers through deep time, and a celebration of the planet that endured so much to become the world we know. Earth's origin story is not a peaceful tale. It is a saga of violence, transformation, and improbable survival. But it is also a story of emergence, of a world learning how to cool, how to stabilize, how to hold oceans, how to form crust, and eventually, how to nurture life. And that is the wonder of the Hadean. A world that seemed determined to forget became unforgettable, not because it left us clear records, but because we learned how to read the silence between the fragments.